feature presentation, measuring dark energy at cosmic noon with HETDEX with the help of machine learning and citizen scientists. Our guest speaker tonight is Erin Cooper. She's at the University of Texas at Austin. She was, I'm sorry, I had the script to introduce you with, and it's let me bug out of my screen share. You can go ahead and get yours up while I.
Yeah, I've got it. I've got it, Stephen. Erin's a research scientist at the University of Texas at Austin. She's the data manager on the HETDEX experiment and the software developer of HETDEX-API and the HETDEX JupyterLab. She has her PhD in astrophysics from the University of Toronto, and her main science interests are in galaxy evolution and large-scale structure. So thank you very much for agreeing to come and share your passion with us, Erin.
Right. Thank you. Yeah, thank you, Don. Thank you, Stephen, and everyone for having me here today. I'm really excited to talk to you guys about the best telescope in Texas and the biggest telescope in continental US. So I'm excited to tell you about HETDEX, which is an amazing project that's been going on for a few years. So just to do a check, am I good with the screen sharing and everything? Does it look good?
Screen sharing is good. And just a real quick procedural thing. Erin has mentioned that if any of you have questions about what she's talking about as the meeting goes along, if you could raise your hand electronically, we'll make sure we try and see you with that. And also just drop a real quick note in the chat so we see that you have a question. And she's willing to take questions as she goes along. So
yeah, if there's anything that you are really wondering about, just feel free to interrupt. It's happy to have a pretty informal conversation here. So yeah, I've been working on HETDEX for quite a few years now, and I'm the research scientist at University of Texas at Austin. And I manage all the data. I help to keep track of it and allow our over 150 users to access our data by creating a whole computing environment for it. So today I'll just really be talking about what the survey is and a little bit about how we're using machine learning and citizen scientists to help us handle some of the immense amount of data that we get with HETDEX. So we're starting here with our beautiful Hobby Eberly telescope. It's a 10-meter class telescope in West Texas at the McDonald Observatory, and it's only a 10-hour drive from Houston. So if you haven't been there yet, I highly recommend it. It's one of my favorite places on Earth to visit. And they have a really wonderful outreach program at the McDonald Observatory where they have star parties multiple times a week, and you can also go on tours during the day to go and see the Hobby Eberly telescope from the inside, which is a pretty incredible telescope. You can see how big it is here. And let's get to the next. Yeah, so this is a nice cut through to see what the HET is actually like on the inside. And the instrument I will be talking about today, where we get all our data from, is called VIRUS. And VIRUS is a massive instrument located, there's a whole bunch of spectrographs located on the side of the telescope on both sides, where it is fed light from the sky. So the HET is an interesting telescope in that you cannot tilt and tip it as you would with regular telescopes. It sits on this big round circular concrete pad that actually can rotate. And so that's where you get most of your sky coverage from. And there is this tracker up top where we can actually control where we're pointing in the sky. Sorry? Oh. Okay, so basically, it's been equipped with this instrument called VIRUS to do the HETDEX experiment, which is to basically map out a million galaxies at a distance of 10 to 12 billion light years away. And I'll get into how we're actually going to go about doing this in a few more slides, but I just wanted to show virus a little bit more, because this is really an incredible instrument. It is the largest astronomical instrument that exists right now. There will be bigger ones as we see the Giant Magellan Telescope and other large telescopes come online. But it is a instrument that is an array of IFUs, integral field units. And what the IFU provides is not just an image of the sky, but spectroscopy and imaging of the sky. So what it's composed of is each one of these holes on this plate consists of 448 fibers. And so these fibers are looking on the sky, and here they are mapping a galaxy, for example. And so in each one of these fibers, the light goes down to the side of the telescope, and then it gets broken down into a series of, broken down into a bunch of wavelength packets. So we actually get spectral information from it. So every observation we get 33,000 fiber spectra. And what we actually do is we take 3 exposures so that we fill in these gaps that you can get in between the fibers. And so every 20-minute HETDEX exposure, we get 100,000 spectra of the night sky, which is an immense amount of data. Every one of our observations is about 20 gigabytes of data. And to put things in perspective, here's a dude, and you can see how massive this instrument is. And so the great thing about a IFU is that you are getting information in both the spatial dimension and you are getting information in the wavelength dimension. And this is, typically we think about light in colors, right? I'm sure if you put a filter on your telescope, you can put different filters on. You might put a filter on to see H alpha in the nearby, in the Milky Way. But so what the IFU can do is it can actually provide, many, many different slices of wavelength information. And, spectra are just rich with information for astronomers. We can figure out, in a galaxy, we can learn what the stellar populations are in the galaxy. We can learn about what the gas is doing in the galaxy. And on top of it, because light gets redshifted, because of this amazing quality that light travels at a finite speed. And so the longer it takes light to get to us, the more that the light gets stretched by the expansion of the universe, that what it offers us is also a way to measure the distance to an object. So this is why it was designed, is basically for any galaxy we find, we can know its position on the sky, but we also know its distance. And so that gives us the power to make a 3D map of the sky. And that's the ultimate goal of HETDEX. So just to show you an example of what observing a large galaxy with HETDEX, with virus looks like, we've got this observation from M101, the pinwheel galaxy. And so on the left is a false color image just made from a few wavelength slices of our data cube. And then in the center, what we're doing is we're scanning, sorry, try to take those things off. We're scanning in wavelength space. And I've pointed out with the arrows 2 regions of the galaxy where we're getting some spectral information. So every pixel you see, we're getting spectral information, but just 2 examples of that type of data cube that you're getting. So in the center, it's looking at the central region of the galaxy, where the bulge is, and we have a lot of older stellar populations. And, we can basically say how old the stars are in this region just based on this spectrum right here. But then if you look at the spiral arm region of the galaxy, it's a different story. We're seeing these really bright emission lines that light up the galaxy as we scan through it. And that's because we're getting a lot of ionized gas in regions where we have a lot of massive star formation going on. So the key reason virus exists is to try to find these emission lines. They provide this great benefit where, you might not have that much continuum light in a galaxy, but that one line where you have emission due to ionized gas, it just spikes up your it spikes up the signal to noise. So you can see as we go through once again through O2 how the galaxy lights up. So that's the key feature is to identify these emission line galaxies for HETDEX. And so why do we want to do this? Well, we believe in this Big Bang model. All of our, the current paradigm that we're in is that we believe that the universe, started 13.7 billion years ago, and it went through this period of inflation and then eventually cooled down to the point where radiation was emitted, and we can then observe it. And we see it in every direction we look. We see the radiation from the early universe in the cosmic microwave background. And so the amazing thing about the cosmic microwave background is no matter where you look, it's basically the same. Now, if you subtract off that energy level that we see that is constant everywhere around us, we see these very small perturbations in the cosmic microwave background. And so this is basically, the beginning of these early mass, matter, and energy perturbations are what lead to the structure formations that we see today. So there's differences between overdensities in the red and underdensities in the blue. And then these differences in the density eventually lead to the galaxies and structures we see today. This is a cosmological simulation of galaxies at present day. And so this acts as a fingerprint that we can use to trace cosmic time. And the rate at which these structures are moving away from each other indicates, locally, like in our present day, it indicates that we see an acceleration in the way that galaxies are moving away from each other. But we really don't know how it comes into play 8 billion years ago or 10 billion years ago. So that ultimately is what HETDEX is trying to do. Another way to look at it is this cosmic time scale that you've probably seen before, that, we start with the Big Bang and these initial mass energy perturbations. And in the regions where we are dense and we have more gas, that's where we start having the first stars form and then the first galaxies. And what we say, the early universe, we say is dark matter dominated. But at some point, the universe has become dark energy dominated. It's certainly dark energy dominated today. We can see that accelerated expansion. But what we really don't know is what role dark energy had to play in this in-between time. And so that's where HETDEX is looking. We're trying to look at these galaxies at a time when, the redshift, if you think about redshifts, it's a redshift of 1.9 to 3.5. And ultimately, what we can do is we can look at the distribution of galaxies, and then we can determine what role dark energy played. And so that's the goal of HETDEX. Stop here if anybody has any questions about that.
I have 2 questions, if you don't mind.
Sure. Yeah.
Did I hear you correctly that the primary mirror of the telescope cannot move or does not move in declination?
It does not, no.
Okay,
Yeah.
I just want to make sure I heard you right.
Yeah.
And also, I see on this page here, it says, most high redshift galaxies that have been found so far tend to be massive and occupy the most dense regions. I've never heard that before. Is that a discovery from HETDEX, or is that something that I'm the last one to hear about?
It's generally common that you have the most dense regions have the most massive galaxies because they've had the longest amount of time to evolve. So they're only going to detect sort of like in here, it's these pockets here where you get the most massive galaxies. But really what you want, it's a great question that you asked, but this is our whole main reason is we don't want just those galaxies. We want more. We want some of the ones that are in the less dense regions. We want to measure all the distances between all these objects to get the clustering.
Okay, great. Thank you.
Thanks.
One other quick question.
Okay.
I hope it's quick. As far as the virus is concerned, it looked to me like all of those heads are fixed. Is that correct? In
the plate here?
Yes, in the plate there.
Yes, yeah. So they're all fixed in the plate relative to each other. What does move is this tracker up top. So the tracker can go up and down, and that's all it can do is go up and down. And so the whole telescope can turn. It's really cool. I've actually controlled this thing where you can actually turn it on the bottom. So it can turn and then it can go back and forth. So in many ways, HET is really good for surveys because of this, because it can only look at something for so long. It can't do a really, really long track across the sky, and it can't look everywhere. You know, it can't go very low in declination. It has a very limited view, so that's why it is well designed for a survey like HETDEX.
So I guess because you mentioned that you're taking 3 images, you're able to integrate in between them, in between the heads, and so at some point are you actually making an aggregate picture, or is it just data?
Question. When we do the dithering, it's actually to just get in between these fibers. Like, so there's this grid of fibers, and so that you have complete light coverage in between those fibers. What is interesting about virus is there's actually gaps in between each one of the IFUs. It's a gap of an arc minute between each IFU, and each IFU itself is an arc minute by an arc minute. And the design of that was on purpose, because what we actually want to do is cover more sky. So we're optimized to collecting a larger area. The cosmologists who work on our team say it's actually fine to not have that data in between. So we call it sparse sampling. So it allows us to cover more sky. It's a great question.
All right. Well, you answered my question. I appreciate it very much. I was a big when I was at McDonald last year. I asked a question of the docent, and they were like, "Oh," and you actually were able to explain what I wanted to know.
Well, I have a slide on it, so you've already covered some later material in my talk. Then.
All right. Thank you.
Another question. You said you could tell how far away or how quickly the galaxies are moving away from each other. I was thinking all we could do is tell how much they're moving away from us, or is that one and the same?
Well, so with the redshift, with when we talk about these galaxies that are really, really far away, basically all the motion in that is the expansion of space-time. So certainly nearby, that's what we can only measure, is the relative distances to us. But once we get to these really, really large distances, it basically that is such a small scale that it doesn't even come into play, our relative distance, because we're leaping huge amounts in wavelength space because of the redshift, because of the expansion of the universe. So yeah.
So these galaxies that are far, far away, you can tell that they're accelerating away from each other?
Well, these ones are mostly just expanding. They're expanding with space-time. It's the ones that are really near to us that we've been able to tell that the expansion is accelerating. So HETDEX isn't really looking at that, because we're trying to look at stuff that's really, really far. Where we have seen it is by using supernova in nearby galaxies. We've been able to tell that everything's moving away from us, and it's moving away from us at a faster rate. So they're 2 different distance measures. So really, we're doing something on a much, much larger scale and a much longer distance.
Okay. Thank you.
Thanks. Okay. So, right. So this is where we found distant galaxies in the past. Hubble Space Telescope has been amazing at, finding all these incredible, really faint, distant galaxies. But the problem with Hubble is to get this image, it's, several days, several orbits, several days of exposures on the Hubble, and the size of it is very small. So this Goods North deep field is, about a quarter of the moon size. So it's not going to provide the volume that we need in order to map out enough galaxies to see this large scale structure. So this is not what we have. I will show you our ugly data. I think it's beautiful, but there is a certain galaxy that we can actually find quite efficiently. And so this is what Virus was designed to look for. It's designed to look for galaxies that are called Lyman alpha emitters. And these are galaxies that have hydrogen gas in them. And behind, within the hydrogen gas, there are stars, a lot of young stars forming, and a lot of UV radiation. And then that radiation gets reprocessed at the Lyman alpha lines. And so the incredible thing is here's the continuum of the galaxy, this red line. It's very low signal. You would barely see it in Hubble. But what happens is you get this massive boost in the intensity at the Lyman alpha line. This is one distinct line where you're seeing one in the hydrogen atom, you're seeing a jump in the electron and a release of energy. And it's providing you this really high signal to noise at just this one wavelength of information. And so we can efficiently observe these with virus in about 20 minutes, which is excellent because then we can cover a lot of sky. And the good thing about having an IFU is because we've got all of this spectral information, so all this information at different wavelengths of light, depending on where this line happens to fall, we can tell what the redshift of that galaxy is and thus what the distance of that galaxy is. So it's kind of this beautiful system that boosts the light so we can actually see it, and then at the same time allows us to detect the distance to it, providing a nice 3D map. And so some examples of what these LEEs might, what they look like nearby are some of these really small irregular galaxies. We don't see this type of hydrogen gas in massive galaxies. It's basically all radiated off. It's all ionized. You don't get this light anymore. But we do see it in some of these low mass nearby galaxies. So HETDEX basically wants to find as many as these as possible. We need 1 million of them. That's what we are, the equations, the theory says we need about 1 million of these in order to get the numbers for the cosmology to work. So we're covering a great deal of sky for this. I like looking at this projection, comparing what it looks like looking down on Earth compared to looking up at space, just to show how much of the sky we are actually looking at. So we've got two fields. We call this, so in the red here, it's called the HETDEX spring field and the HETDEX fall field, which, depending on what time of year it is, that's when we're going to be collecting our data. And so we're ultimately going to tile 540 square degrees of the sky, but we don't need to do perfect tiling. We can have these gaps. And so when you see our data, you can see that there's actually gaps in our coverage. And so this is just sort of an example of some of our tiling. One of our legacy fields is Cosmos. And this one, we're actually trying to get some complete coverage. So you can kind of see these donuts, but most of our survey data will just have a lot of gaps in it. And so we began observing in 2017, and we're actually going to be finished our main survey operations this year. We just put in our final observing proposal. So we're super happy about not having to write more observing proposals. And we're starting to see results, which is amazing. You will hopefully be hearing about these coming out in the next few years, our exciting stuff that's happening. And this is just an example of a slice in redshift space. So like in the line of sight direction, all these green points here are low redshift galaxies, and then these red points up here are Lyman alpha emitting galaxies. These are our distant galaxies, which in it, there's a lot of equations involved to figure out the sensitivity, but deep within that, it has the cosmology built into it. But ultimately, this is what our data looks like. We're trying to look for these blips of signal on our IFU data. So with the IFUs, we basically have spectral data that gets projected along our CCD. So we don't ever get an image of the sky. We don't get an image of the galaxies. What we get are our fiber spectra where we can see spectra along this dimension. And so these are examples right here of Lyman alpha emitting galaxies. And so we've developed code to try to find these. But we've got an immense amount of data. So right now we have 600, it's 600 million fiber spectra. And each of those fiber spectra contains 1,000 data points in the wavelength dimension. So, we're going to hit a trillion data points at some point. So it's a ton of information that we have to parse, and like 99% of it is noise. So it is really like looking for a needle in the haystack. So there's a lot of ways we're trying to go through some of our data, because we do have a lot of artifacts, and there are things that we have to weed through.
With this kind of amount of data, do you use, I dare say, artificial intelligence to look at it?
We do. So that's a bit of the topic here. So yeah, we have pivoted, and we are using AI in all sorts of ways. So I have a few slides on that I'll share.
What percentage of all galaxies are Lyman alpha?
Ooh, that's a tough one. So when we look at galaxies that are in, say, the Goods deep field, and we confirm that these are galaxies at the distance as the Lyman alpha emitters that we know of, it's only about 10% of those are Lyman alpha emitting galaxies. But if you go to lower mass, there are much more galaxies that have Lyman alpha emitters. So I would say we don't exactly know, but what we believe, and this is the reason we're doing the survey, is that there's many more Lyman alpha emitting galaxies than, say, these very massive galaxies that are out there. So they're easier to find. There are more of them, and in the data ultimately.
So, question about the amount of data that you're going to have when you actually get it all on board. How many terabytes of data are we talking about?
Yes. So our current data storage is at 350 terabytes of storage. And you know, some of this is backed up data, like, you know, data from older releases, but, you know, currently it's 120 terabytes that our users access at any moment. And so what we make sure we do is allow that data to be, you have to make it very easy to query and access and be efficient, because it takes up a lot of computing power. And we're very lucky that we have a great relationship with the Texas Computing Center at University of Texas. So TAC, they allow us to store our data there and use an immense amount of computation. So everything we do is with supercomputers these days.
Could you quickly just go back over what this, how this Lyman alpha emissions data is important vis-a-vis your objective?
Yeah, well, the real benefit is that it helps us to efficiently find galaxies that are very distant. So these are galaxies that are 10 to 12 billion light years away. If you were going to try to find the distance to these galaxies through another telescope, you would have to do a 4-hour long exposure on, you know, Keck, or, you know, one of these big telescopes in Hawaii. And so the Lyman alpha emission does this amazing thing where just at this one wavelength, it creates an immense amount of energy at one specific wavelength, allowing us to find that one galaxy, to find the galaxy and assign a redshift to it. So
the amount of energy you pick up tells you its distance from us.
Exactly. The location in the spectrum. So this is from another talk, but I just wanted to show some examples of what our galaxies look like. So this is the Lyman alpha emitting galaxy at a redshift of 1.99. So that's, you know, something about 10 billion light years away. The galaxy in the imaging, you can barely see it. This is from the Subaru Space Telescope. And then this is our data where we collapse it just at that wavelength. So this is actually in the spatial dimension. It's just, if you've ever used an H-alpha filter, it's basically a filter just at the line where we have detected the emission. And so depending on where these lines fall, I'm just pointing out Lyman alpha in all these different systems, depending on what wavelength it's at, it tells us how far away it is. So the longer the wavelength, the higher in number, the redder it is, the further away the object is. And so the beauty is we're getting the distance to all of these objects. So we're not just getting a map on the sky, we're getting 3 dimensions on the sky.
So is it fair to say that you're looking at the Lyman alpha because it happens to be the brightest thing in the spectrum for that object? Is that right?
Absolutely. Yeah. Otherwise, you just wouldn't see it. Some of these we barely see in this deep imaging here. You can usually see it in Hubble or James Webb. We're looking at James Webb data of our objects, which is awesome. And you see it there, but that's James Webb will never be able to cover the type of area that we are covering with HETDEX. So the real goal is finding 1 million of these. So we're all about statistics with HETDEX. So it's not
so efficiency is one of the important aspects of this design.
Absolutely. It's covering a huge amount of sky. So 540 square degrees, it's over half the size of the United States. If you flipped it up and you pasted the United States on your sky ceiling, like it's a huge amount of area that we're covering. I put this here because we are all about statistics, and this is what the average Lyman alpha galaxy looks like in HETDEX. Very, very little continuum and a huge spike in data. But what we can actually do is stack. Here we stack a sample of 50,000 galaxies. And then what we actually see, this is light from the galaxy itself, or so from the average Lyman alpha emitter galaxy in HETDEX. We're seeing all these bumps and wiggles in the spectrum. And what's actually incredible here is every single bump and absorption line that you see here is telling you something about the galaxy. So we're not just seeing Lyman alpha, we're seeing Lyman beta in absorption, gamma, delta, we're seeing, so the Lyman series, we're seeing all these stars. What we see with these ones, they're called P Cygni profiles. We're actually seeing gas outflow around the stellar populations inside the galaxy. So we are finding them is the point. Although, ultimately in a single one, you would never detect the continuum. But if you stack them all with statistics, you can boost your signal by a factor of 1,000, which is pretty incredible. And so we're doing lots of interesting things with statistics with HETDEX. It's stuff I wasn't even thinking we would be doing with it.
Maybe you've already answered this question, but why Lyman alpha? Why are these emitting in Lyman alpha and not H alpha or something else?
They probably are emitting in H alpha, but the great thing, Lyman alpha is going to be the brightest. And the other thing that's great about it is Lyman alpha gets redshifted into the optical. So Lyman alpha is actually an ultraviolet line. To see it nearby, you have to put a telescope in space to see it. So it's sort of this opportune line because, we have a lot of telescopes that are designed in the optical regime, and we happen to have transparency to the night sky in the optical. So it's the primary transition in hydrogen. So you get that you get the brightest line there as well.
Thank you.
So if it was a space telescope, would you pick a different frequency?
I mean, it depends on what instruments are on it. So James Webb is space telescope is designed to operate mostly in the near infrared and the mid infrared, and so they are having a blast looking at all these amazing molecular lines that happen to be in there. And ultimately, you would not perform this type of experiment with a space telescope just because you just can't get the same sort of volume. But certainly, there's other lines you would look for if you're in a different optical regime. The near infrared is providing so many other interesting features. But for us, we like Lyman alpha because it's common in these low mass distant galaxies, and it allows us to observe many of them efficiently. And one thing that I'm getting really excited about is we're also finding these things that are called Lyman alpha blobs. And so these are super large, basically regions of ionized gas that that they're much larger than the scale of a galaxy itself. They're, 2 to 3 times the size of the Milky Way. And they come in all sorts of shapes and sizes, and they're basically the most massive structures that exist in the universe. And HETDEX is great at finding them because they're relatively rare, but of course, if you cover enough survey volume, you're going to find a lot more of them. And so this is just, these are some of our HETDEX Lyman alpha blobs, just to say these are 30 arcsecond postage stamps. And so there's an example here from, forget where it's from, I think Subaru. And this is just an artistic impression. If you happen to go deep into the system, what would be going on? They don't exactly know everything that's powering these Lyman alpha blobs. We're going to be helping to learn more about them with HETDEX. But there are things like supermassive black holes that are in their active growth phase where they're feeding off of a lot of gas. They have a lot of outflows going on. You have a lot of star formation happening in there. Most of the Lyman alpha blobs either have, AGN, these supermassive black holes that are actively growing, or they have a whole bunch of star formation. So a lot of them appear to be this is another one of those simulations, large scale structure simulations of where we have, galaxies. It looks a lot like, if you look down on Earth and the light pollution patterns, but it's actually a cosmological simulation. But these Lyman alpha blobs are super cool because they're showing up where we have the most dense regions in the universe. Other people are finding that they map to these overdense regions. So it's going to be a pretty exciting study with HETDEX. We're really excited about that. And so now on to how we're looking for help from you guys and how we're getting help from other unusual places that astronomers really weren't looking for help before. But we've been asking citizen scientists to help us out with some of our classifying. I don't know if you've ever gone to Zooniverse, but it's a pretty cool place. There's all sorts of different science programs where people are asking citizen scientists to come help and classify their objects. So what we've done is we've made a few workflows that we've tried to make them binary. So it's basically as easy as as easy as Tinder. You can classify your galaxy, swipe left or swipe right, depending on which workflow it is. And we're getting a lot of activity from Zooniverse, and we're actually really using the classifications we get. So what we do with this sort of classifying, we get between 10 and 15 classifications from citizen scientists, and then we take the average to help classify our data. So that's called Dark Energy Explorers, and there is an app for your phone, or you can just do it on a website. And we've got almost 2 million classifications done and 15,000 volunteers. Super awesome. And so it turns out the way that we can best use some of the classifications we get from machine learning is to combine Dark Energy Explorers with machine learning. So this here is one example of unsupervised machine learning. We use it in a lot of different ways. It's a pretty interesting technique where you put in an array of data and you do it for a whole bunch of sources, and you just let the software try to find features that are common in it. And it might not necessarily be something that you look for, but what we found is that if we allow our software to try to cluster our data, and then we match it with the classifications we get from our citizen science classifiers, the Dark Energy Explorers, we can then figure out what parameter space of our data set we should throw away. And so this is work done by Lindsay House, who's a graduate student at UT. So the colors here, these Dark Energy Explorers probability is basically the average we get from the citizen scientists. And so the citizen scientists have said, this region has, a lot of bad data. And the machine learning decided to cluster a bunch of stuff over here. And when we looked into it, we could see that most of it was was artifacts and data that we shouldn't use. So in combination with citizen science and machine learning, we're able to find artifacts in our data. And we're really using machine learning for all sorts of things. This is an interesting one. Another type of unsupervised learning where you put in a spectrum. So we've basically put in something like this, just this spectrum goes into the TS&E, the unsupervised machine learning, and we see how it clusters. And the interesting thing that it does, we've colored it here based on redshift, or the distance to the galaxy. What we find is the machine assigns a redshift to our objects without knowing anything about them, not knowing what stellar populations are in there, not knowing what the gas is. So it's pretty incredible how we're finding different ways to use machine learning. There's also, so it's not just redshift, there's also some information about the line emission. The amount of line emission will vary based on where it is clustered. So that's quite interesting. Other ways we've been using machine learning is we've been working with this company, which we're really thankful for. Basically, it's this startup company. They came to the Board of Visitors meeting in Austin and helped set us up with this, with their software. And they've been allowing us to use it as part of their AI for Impact program. And then in return, we test their software. But what's kind of incredible is to see how AI is really now a tool, like an off-the-shelf sort of tool that you can start using. It's become so mainstream. I mean, and now available. You know, in the beginning when we were doing it, even 5-6 years ago, it was a very new subject. You had to do everything yourself, and you had to assign labels, and it would be actually kind of tedious. But I just wanted to sort of share one part of our you know, machine learning pipeline. So we now we use this software. This is a website that they have created to upload our data. And this is just an example of what our data typically looks like. It's just a bunch of dots in our images. And there are artifacts, but for the most part, it's just dots. But we need to find a way to get the dots, to get any artifacts out of our data. So just over here, these are some examples of artifacts. And what this software does is it searches through hundreds of thousands of our images, and it says, okay, I'm going to find all the ones that are similar to that image. And then in a matter of minutes here, it basically pulls up, I'll just speed through it a bit because it's a little slow, but it pulls up all of the data points in our you know, in our detection database that are similar to it. And then it allows us to take all of those and apply a label to it. And so this is where machine learning, if you're familiar with it, there's unsupervised machine learning, and then there's supervised machine learning. And supervised machine learning tends to be more robust. It allows you to apply a label to your data set, and then in turn it can go through and go through all of your data and try to find like things. So this type of classification is now part of our pipeline. Just showing, I think, another example, but nobody wants to sit around, but just to show how it might find another object, and then we can classify that and put it into a labeled system. And we are now using this as our pipeline. It has helped to identify hundreds of thousands of artifacts in our system that, you know, we found probably 80% of them, but not all of them. And so this really helped us to clean up our catalogs and in a relatively fast way. We didn't have to go through 20,000 images to apply the labels. We were able to make labels quite quickly. And so I'm just showing sort of some examples of what kind of labels where we try to, like, these are good sources in our data, and then this is bad sources. So it helps us to apply, to find artifacts. And another thing that's really interesting is it's really good at finding streaks in our data. So for example, this is what a meteor looks like in our data. We have something like 88 meteors in our data. And what it's also really good at finding is satellites. This is what a satellite looks like. I didn't put an image in here of a satellite, but we're actually finding, it's quite disappointing. We're finding a lot of satellites crossing through our data. So we've, I think, found something like 600 observations have a satellite crossing through it. And it's an average of 10% of our data has a satellite crossing through it. Fortunately, it only affects about 1% of the data overall, and we are finding ways to just block that data out. There are other people who have a satellite going through their data, and you know, they have to throw the entire thing out. I just put this image here. Just of course, it's embellished, but you know, I think we're at something like 8,000 satellites, maybe more, orbiting Earth. So we're seeing that increase with time. And I've got a little chart here just showing how the number of satellites in HETDEX data has been increasing over time, quite correlated with the number of satellites that have been launched into space.
Are you trying to make us feel depressed about the satellites? Is that it?
You know, I think everybody has to be a little bit upset about this, and I think people should be making some noise. So yes, I think I'm a little depressed by it, and I'm not going to hide it. But it's just another thing that we wouldn't have been able to do this without machine learning helping to find it, because they can be tricky to find. When you have an artifact that only affects 1% of your data, you don't always find it that easily. And so the machine learning has really become an important tool to find certain features like satellites or meteors or other artifacts in our detectors. Yeah, so on the depressing note, let's look back at the HET. The HET is an incredible telescope. Really, it's, you know, at your doorstep, 10 hours away. It's something to be really proud of in Texas, for one. But if you want any more information about HETDEX, we've got a nice website, HETDEX.org. I've also put up the QR code if you want to scan that and become a dark energy explorer. That would be awesome. We're always happy to have more help on the project. Thanks.
Thank you. It sounds like your system works very well. A very impressive, creative concept, creative system. But what is that telling you so far about dark energy?
Well, so we don't have the measurement yet. So the survey is we're almost done. We're 90% of data collected right now. But the measurement itself is complex. We have a lot of work that we have a large team working on. So we don't have our results quite yet, but we should have it in 2 to 3 years. Yeah.
Erin, there were other surveys that are looking at different distances on the cosmological spectrum there. And yeah, if you don't mind going back to that slide where you showed the tunnel, where are they at? I remember from presentations about this work some years ago that there were maybe competitors is too strong a word, but that there were farther back in the actual tunnel from 13.7 billion. Yeah, that one. Some were looking at different distances. Have they gotten results?
Well, there certainly there are, I don't really know about the dark energy impact, but I mean, that's basically what DESI is trying to do. So SDSS and EBOS are very large spectroscopic surveys that happen relatively low redshift. And so they measure all the clustering and the cosmology very well. But then there's DESI right now. So DESI is going from, I mean, basically 0, but I think the most important part is up to like 1.2, where they're going to be doing the measurement. And I don't think they have a result out, but they will soon. And then they're going to try to push for where we are. So we have to get our results out.
And you guys are 3 to 5, 3 to 4, something like that?
Yeah, redshift 1.9 to 3.5.
Okay, thanks.
Thanks.
I heard I read an article, I guess it was today,
Yeah.
which I don't really quite understand what they're talking about, but some guy, I think in Russia, has come up with a new mathematical way of analyzing gravity,
Yeah.
and looking at gravity. And I was wondering if that has anything to do with what you guys are looking at.
You know, we are totally living in the paradigm that we call it lambda CDM. It's this cosmological model that fits, you know, all these elements of our data. But there certainly could be other explanations. And I mean, I'm not familiar with this. And honestly, that sort of like stuff is even over my head. But the interesting thing is, you know, HETDEX could throw lambda CDM out the window. We may see something that doesn't make any sense at all. And that's what's really exciting about this type of survey. But yeah, there's a lot of theories on you know, modified gravity. There's lots of different ideas out there about, you know, different cosmologies and cosmological models. But I'm not familiar with them.
That's because it's science, so you know it'll change in a couple of weeks, right?
Well, I mean, it has to. We have to be open to it.
That's
I see a couple questions in the chat. I'm wondering, does anyone want to bring up any of the questions they put here? How long have you been using machine learning? You know, we've been using it for probably 3 to 4 years, and it continues to surprise us. And Pradeep says the February issue of Space Telescope had a feature on the DESI survey studying BAO. So I guess we kind of just talked about that. They're at this point we're complementary, but we're doing very similar things. It is the BAO that we are measuring, and our result will be about measuring the BAO, the baryonic acoustic oscillations. Oh, and Deborah, that's a good question. Do you spot check the data from machine learning and citizen science manually to assess accuracy? Yeah, absolutely. We do a lot of visual checks, and we try to talk about the accuracy of the citizen science. And ultimately, you know, something we found was that it was better to combine the citizen science with the machine learning, and that gave us the highest accuracy because our accuracies weren't really high enough just based on the citizen scientists for the questions we were asking. We're asking pretty tough questions for the citizen scientists. We're right now we're asking if they think our data is real or not, and a lot of it is pretty tough. So we find the combination helps better.
So I think if I was to kind of sum up the situation, I mean, you're having to collect a huge amount of data because we have a very big problem and a very big universe to try and understand. I mean, that maybe that's oversimplification, but it seems as though in order to put the whole model together, we not only need to know what's happening in our, you know, easily time reachable realm, but also going all the way back. And right now we've got slices, but we don't have a good continuous understanding of everything yet.
Yeah, absolutely. I mean, and you know, we can only hope that once we do this measurement, someone else can do the measurement at a further distance, and we can just get more data points. But yeah, it's really the design of HETDEX was to, you know, make good use of the HET telescope and the design that it has, and develop this really innovative instrument to as efficiently as possible find these distant galaxies. You know, before we released this catalog, we've released about a year ago a catalog of 50,000 Lyman alpha emitting sources. And before that, I think the largest catalog, actually before that, probably all the known redshifts to exist in that redshift range was maybe 10,000. So, we're going to be just increasing the number of we call them redshifts, because when you can secure a distance to a source, you really are able to then, make statistics with it. You can do your science with it. You can talk about we talk about things called luminosity functions and mass functions, and you can think about statistically how galaxies evolve and the mass and energy have changed as a function of time. So knowing that distance really well is important, and that's the really the great thing about virus is it can pinpoint that redshift and that distance.
And and to try and kind of anchor this back to astronomy history, I mean, it's been not much longer than 100 years ago when Hubble first recognized that the galaxies weren't little groups of clouds in our own Milky Way galaxy. They were actually separate star systems.
Yeah.
And here we are 100 years later, we've got a better picture, but we still have these big gaps we have to fill in.
Yeah, I mean, it was only 25 years ago that we learned that the universe was accelerating. So
yeah, exactly. That's what blows my mind, I have to say.
Yeah.
So Erin, what's next for HET if you're at 90% data collection, then 100 follows that, and then what follows that?
Yeah, that's a good point. I don't know if I can pull up my skip slide. How do I? Oh, I don't know. So there are gaps in our data, and what will ultimately happen is certain regions are very interesting for they're very interesting for galaxy evolution, and so the plan will be to fill in the gaps for some of these regions. So there's, I don't know which slide. There's Cosmos, which we will continue to fill in. We'll want to fill in all of these regions, but then in this fall field, this is a very rich field. It's called the Stripe 82 field, and we have a wealth of infrared data and all sorts of different data in that field. And so what we'll want to do is basically fill in all of the gaps. We don't want just the pattern, the tiling that HETDEX has. So that'll be some of it. And then there are so many astronomers that are waiting for time on HET. So HET doesn't just have virus. It has it has another spectrograph that operates at longer wavelengths. And then it also has a planet detecting instruments. So people are going to be wanting to use the HPF, and they're going to be putting more time. So there's a lot of astronomers that aren't on HETDEX that are looking forward to using that time. But I think we can expect some kind of survey to continue on. We're just getting into it with HETDEX. So we expect that people are going to want similar types of observations from it.
Okay,
Please forgive me.
thank you.
I'm sorry. Go ahead.
No, sorry.
Please forgive me. I'm certain that you said this already, but virus is your spectrograph. I'm correct?
Yes.
And the I in virus stands for IFU. And I missed what IFU was.
Okay. Yeah. So the IFU, it's an integral field unit, and it's the when you have an array of these fibers, we call it an IFU. And so it's not just an image, but it's an imaging spectrograph. And so we get spectral information and we get spatial information.
Got it. I forgot what that was. Thank you.
Yeah. Okay. I don't know if there are any other questions.
Extremely interesting topic and presentation. You guys are doing very unique work out there, in case you didn't know that. Yeah.
I also want to thank you very much, Erin, for spending your time with us. maybe a little bit more chaotic than you thought it was going to be. I hope.
Oh, I love the questions. I prefer the format where we just get to talk about it, and I've loved everybody's interest in our project and the instrument. So I'm happy to share. Yeah.
Thank you, and I also just want to re-highlight the fact that Erin was encouraging all of us to come out to Fort Davis and really appreciate the jewel we have in our state. I can tell you, I've been out there several times myself, and every time I go out to the McDonald Observatory, I learn something new, and it's amazing.
Yeah, I mean, they do a great job there with their star parties, and it's not most places that you can go and you can get in and you can see a telescope like this. So they'll let you in. I think during the day they have certain tours, and so you can actually visit the HET and the other telescopes at Mount Locke. And then they have a visitor center. So there's lots, and it's a great place to visit. You can go hiking in Big Bend, and there's stay at the State Lodge nearby. It's a great place to visit.
See the Marfa lights, right?
Yeah, I haven't been to Marfa actually. Yeah, I've heard it's cool though.
Well, I just want to say thank you again, and we really appreciate your time. And,
thank you.
I just have to say, I personally, I've always felt, the universe is so much bigger than we are, and it's hard to comprehend. Yeah, you just made my problem bigger. Thank you.
I know. It is kind of wild, but it's kind of neat that we're covering so much of the sky that not just our survey, but so many DESI, all these other surveys. We're really seeing so much of it. And with JWST, it's a whole new ball game. We're seeing different views that we've never seen before.
Yeah, we all need to get the AI stuff to get rid of the satellites from our images. Thank you very much.
I don't know if it affects you, but it was definitely alarming to see the numbers going up with time. Yeah.
Well, I think that's a problem that's going to continue to be worked going forward as well, because it's as you say, the more data you can provide that says, hey, this really is a bigger problem that correlates almost directly with the number of satellites,
Yeah.
If there's anything that we can do to help with that, just let us know.
Yeah, and that's another way to get internet everywhere.
There's lots of other ways to get internet everywhere.
Yeah, I mean, everybody doesn't need to be able to stream, Netflix constantly everywhere. I think that's some of the reason people are saying, hey, okay, everybody can have internet, but they don't need to have, these incredible blazing speeds. Right. So, because it will provide internet to the whole planet, which is the benefit of these satellite constellations. So there's some benefits to it. We just need a balance.
All right. With that, I'd like to thank everybody for joining us tonight. And I just want to remind you that next month we have a little bit of an unusual situation, in that we will have our main meeting on the 1st of March, and the novice meeting on the 6th of March. It's Thursday, the 6th of March. That's just the way it turned out. And please join us then. And thank you again, Erin, for your great explanation of what's going on with HETDEX, and we hope to see you. I hope to see you out in Fort Davis.
Yeah, I'll be at the BOV meeting. I see Bill will be there. Yeah. Okay. Well, thank you so much for having me. I enjoyed it.
All right. Thank you all.
Thank you.